My dear students, I am extremely happy in seeing you all today through this program. So, in physical chemistry, you might have studied a lot of topics in your undergraduate level. Today, we are going to see a very important topic called group theory. This topic, group theory, is also been called by other names like symmetry in chemistry, beauty in chemistry. To understand this topic, the students should listen to my lectures very carefully, because it involves some imagination as well as some deep thinking. So, simply by looking into the books or any other reference papers, one cannot learn the topic group theory. It involves a lot of imaginations, and moreover, first if you have a proper exposure to the topic, then if you listen to some other books or some other lectures, then only you can have a proper understanding. Now we shall see what is called group theory. So as I already mentioned, this topic is also been called as symmetry in chemistry, beauty in chemistry, or group theory. Nature provides countless examples of symmetry, which is one of the most important pervasive concept in the universe. Moreover, we the human beings, we have developed a lot of designs, structures in our day-to-day life. All these structures and designs which we have evolved are utilizing the concept of this group theory or the symmetry in chemistry in more or less important constructions. This group theory can be viewed in two different ways. One is called the mathematical sense, another one is called non-mathematical sense. In non-mathematical sense, the symmetry is associated with regularity in form, pleasing proportion, periodicity, harmonious arrangements. So these are all the ways by which one can look the group theory or symmetry in chemistry from the non-mathematical sense. Whereas from the geometrical sense or mathematical sense, the same group theory can be analyzed as axis of symmetry, which is a line, center of symmetry, which is a point, plane of symmetry, which is a plane. So by these three means, one can visualize the symmetry from the geometrical sense. Now we have to see one by one. As far as we the chemists are concerned, one of the most important problems confronting is an understanding of the structure, how the atoms in a molecule are related to each other in space, and how these molecules are related to one another in a crystal. For example, in the given diagram, I have given four structures. Structure number 1 is called pyrene, structure number 2 is called phenanthrene, and structure number 3 and structure number 4, I didn't give this name. So I have given the four diagrams or four figures. Suppose if you look into this structure number 1, there I have given numberings for all the ring carbon atoms. So starting from 1 to 10, I have given 10 numbers. Now first we have to see what are called the equivalent positions in the molecule. So only if you are capable of understanding this principle, equivalent positions in a molecule or equivalent positions in a crystal, then only one can predict the properties for the molecule as well as their applications. In this first diagram, pyrene, I have given the exact diagram. There are 10 carbon atoms. Now we have to see what are the equivalent positions in the given diagram. So it is very clear in the given diagram, the positions 1 and 6 are equivalent, and 2, 5, 7, 10 are equivalent, 3, 4, 8 and 9 are equivalent. So there are 3 sets of equivalent carbon atoms in the compound called pyrene. So can you follow? So simply by, moreover, if you want to understand the equivalent positions for a particular molecule, you have to draw the diagram perfectly. So having the equivalent distance, bond distance between carbon and the bond angle equal to 120. So by this way, one can visualize the beauty of the molecule, and also one can understand symmetry of the molecule. Next compound is called phenanthrene. In phenanthrene, if you look into the molecule, here also there are 10 carbon atoms. So I have given the diagram. In this diagram, if you look into the diagram very carefully, one can understand there are 5 sets of equivalent carbon atoms in the compound called phenanthrene. They are 1 and 2 and 3, 5, 8, 10 and 4, 9 and 6 and so on. So there are 5 sets of equivalent carbon atoms in the compound called phenanthrene. Suppose if we look into the molecule structures number 3 and 4, you may think these are all new compounds. It is not the case. So look the molecule with the structure number 3. This molecule is not a new molecule. Suppose if you rotate the molecule to an angle of 90 degrees, so you will be getting the same orientation similar to structure number 1. So now we can come to the conclusion structure number 3 is not a new compound, it is equivalent to only pyrene. Or equivalent positions which you have allotted to the compound pyrene, the same can be given to the compound number 3 also. Similarly, compound number 4 it is not a new compound, it is also equivalent to your phenanthrene. So if you are capable of finding out the equivalent position in a particular molecule, then as a chemist you can predict the properties of the molecule, their biological activity and also their future applications. So it is very useful tool for us, namely our chemists, to understand the usage of the particular molecule in day-to-day our life. Next we have to see what are the different kinds of symmetry elements that are possible. Actually there are 5 types of symmetry elements. They are center of symmetry, which is also called inversion center, identity, rotational axis, number 4 mirror plane, number 5 rotation reflection axis, which is also called alternating axis of symmetry. So we have to see one by one what are the corresponding symmetry elements and what are their applications and what are their corresponding operations. So now after seeing the 5 different kinds of symmetry elements, now we have to understand what is called symmetry. It is a simple definition. So you are studying this concept ever since you have entered into your school days. From 6th onwards, this concept of symmetry is taught in all the schools. For example, if you take a simple molecule like water or any other molecule, one can see the one part of the molecule is liking almost similar to other part of the molecule. So as a layman, one can give the definition for the symmetry as, in a molecule, if one part or if one portion looks similar to other part or other portion, then we can claim the molecule is having the symmetry. So this is the simplest concept or the simplest definition one can give to understand this concept symmetry. But as a chemist, we have to give a detailed account. Now the thing which I have given is called only the layman's view. As a chemist, we have to define properly what is called symmetry. Symmetry means, suppose if the molecule is having more than one orientation in space, which are indistinguishable or which are superimposable one over the other in space, then we can claim the molecule is having the symmetry. For example, if you look into the water molecule, there are 2 structures. So they are given in the diagrams 1 and 2. So from the structure number 1, if you want to get the structure number 2, if you rotate the molecule to an angle of 180, then we will be getting another orientation called structure number 2. So these 2 are indistinguishable. Hence I can claim water molecule is having the symmetry. So after knowing this, the concept or the definition for the symmetry, now we shall see one by one what are called the 5 different types of symmetry elements with the examples as well as the corresponding symmetry operations. So before I take up the topic called the center of symmetry, I have to give one important point. So don't confuse yourself between the symmetry element as well as symmetry operations. Symmetry element and symmetry operations, these 2 are completely different. We should have a clear distinguished understanding between these 2. Symmetry element is the element one among the 5 which I have already mentioned. But regarding the symmetry operation, the symmetry operation is the operation which you have to perform to understand the presence of the particular symmetry element. And moreover, the symmetry element and symmetry operation, these 2 are always going together and they are inseparable. For example, if you want to understand the presence of symmetry elements, one can have or one can come to the conclusion that particular symmetry element is present in the particular molecule only by carrying out the corresponding symmetry operation. Without carrying out the symmetry operation, one cannot tell the particular symmetry element is present in the given molecule. Similarly, if you come to the second case, namely symmetry operation, these symmetry operations cannot be performed on its own as you like. So these symmetry operations should be carried out only with respect to corresponding symmetry elements. Only after the symmetry element we have to perform the symmetry operation. So you know very well, these oxidation reduction processes cannot be carried out separately. Suppose if you want to oxidize one equivalent of A, one equivalent of B should undergo reduction. Similarly, if you want to understand the symmetry operation, or if you want to know the presence of symmetry element, so only by carrying out the symmetry operation one can understand the presence of symmetry elements. Now, these symmetry operations and symmetry element cannot be separated. I can quote number of examples. So, before looking into these the examples, we shall see one by one what are called 5 different types of symmetry elements. First one is called centrosymmetry. So, centrosymmetry is a dead old concept which you are learning even from your 6th standard onwards. Centrosymmetry. The centrosymmetry in a molecule, one can claim the presence of centrosymmetry provided if we move from one corner of the molecule in a straight line through the center, and then if you extend your journey to the other side by an equal distance, if we may encounter or if we meet a similar atom, and if it is applicable to all other atoms present in the particular molecule, then only we can claim the molecule is having the centrosymmetry. Simplest example, you take nitrous oxide. In nitrous oxide, the formula is N2O2. So, starting from oxygen, you move in a straight line, you come to the center, and then you extend your journey to the other side by equal distance. Then once again you are encountering or you are seeing another oxygen atom. Similarly, starting from nitrogen, you move in a straight line, come to the center, go to other side by equal distance, you are encountering the same nitrogen atom. So, starting from nitrogen, you are meeting another nitrogen. Starting from oxygen, you are meeting another oxygen atom. Hence, I can claim the molecule is having the centrosymmetry. Similarly, if you take benzene, starting from one carbon atom, you move in a straight line through the center and then go to other side by equal distance. You are encountering or you are seeing another carbon atom. It is applicable to all the 6 carbon atoms present in the molecule as well as 6 hydrogen atoms. Hence, I can claim the molecule benzene is also having the centrosymmetry. Whereas, if you take our water molecule, in water molecule, if you apply the same principle, one can find very easily there is no centrosymmetry. Similarly, you take methane. So, methane is having lot of symmetry elements, but there is no centrosymmetry. If you take the second example, in the second member in the homologous series, alkane series, first member methane, there is no centrosymmetry. You know very well, methane is having a tetrahedral structure with a HCH bond angle 109 degrees 28 minutes. So, here there is no centrosymmetry. Then if you go to second member called ethane, in ethane you know very well there are 2 forms. One is called staggered form, another one is called eclipsed form. So, in the eclipsed form, if you see this molecule, there is no centrosymmetry. So, in the eclipsed form, there is no centrosymmetry, but if you take the staggered form, we are having the centrosymmetry. Then you take the molecule ammonia. In ammonia also there is no centrosymmetry. So, if you compare ammonia with another molecule called BCl3, BCl3 is also having 4 number of atoms, ammonia is also having 4 number of atoms. The main difference between BCl3 and ammonia is BCl3 is a planar molecule, non-linear structure, whereas ammonia is non-planar, non-linear. In BCl3 also, if you take the molecule, if you look into the molecule, there is no centrosymmetry. So, both BCl3 and ammonia, there is no centrosymmetry. Similarly, you can extend your studies to some other molecule, other common examples. Next example is your ethylene, the parent compound ethylene, the molecule is having centrosymmetry. Then you take trans dichloroethylene, there is centrosymmetry. In the cis dichloroethylene, if you look into the molecule, there is no centrosymmetry. Similarly, you take monochloride ethylene. In monochloride ethylene also, there is no centrosymmetry. So, I can give a lot of example for the same symmetry element called centrosymmetry. But you only if you look into the molecule very carefully, conclusion whether the molecule is having centrosymmetry or not. So, I have given all the familiar examples. Then you apply your mind to other molecules and then you can conclude yourself whether a particular molecule is having the centrosymmetry or not. And this centrosymmetry is given by the letter small I. So, small I represents centrosymmetry. So, after seeing the centrosymmetry, next we have to see the second symmetry element called identity. So, identity is given by the letters or the symbol as either capital I or capital E. So, both are representing the identity operations. So, at the beginning of this topic, I told you for all the symmetry element, there will be a corresponding symmetry operation, and also I told you only by performing the corresponding symmetry operation, we can come to the conclusion whether the molecule is having the particular symmetry element or not. So it is applicable to all other 4 symmetry elements. It is not applicable to the present symmetry element called identity. So if you ask me the one question, sir, what is the operation which you have to perform to understand the presence of the particular symmetry element called identity? Simply I will say no. If there is no symmetry operation at all for a particular element, so you take the molecule, keep it on the table, wait for some time, let it be. After some time, if you look into the molecule, one can come to the conclusion the molecule will be having the same similar orientation in space. So since it is having the same orientation as in the previous case, then I can say the molecule is having this identity as one of the symmetry elements. So by this definition, we can come to the conclusion all the molecules which are existing in nature till today or which are going to be synthesized in future will be having the symmetry element called identity. So whatever may be the structure, whatever may be the complexity for the molecule, whatever may be the number of atoms, 1000 atoms, 10,000 atoms, all the molecules which are going to be synthesized will be having the symmetry element called identity. So simplest, but at this juncture, one may think it is a trivial, it has no meaning at all. The significance of the symmetry element called the identity could be understood only at the end of the topic, that is called your multiplication table as well as the character table. Next, third one is our symmetry element called the axis of symmetry. It is also another important symmetry element. It is given by the symbol capital C suffix n. So n is equal to, given by the formula, 360 degree by theta, where theta is called angle of rotation through which the molecule is rotated to get an equivalent orientation. Now, to understand this particular symmetry element called as axis of symmetry, first I will give the definition. After seeing the definition, we can go to the example. So it is an imaginary axis present in the molecule in such a way, rotation of the molecule along this axis through an angle theta will produce an equivalent orientation. So by this definition, we can find out whether the molecule is having axis of symmetry or not. So after seeing the definition for this axis of symmetry, now we can see the example for this symmetry element called axis of symmetry. So you take water molecule. In water molecule, we know we are having one oxygen atom at the center and one hydrogen on one side and another hydrogen on the other side. So they are given by the H prime and H double prime. So the structure number 1 has been given in the diagram. From structure number 1, if you want to get structure number 2, we have to rotate the molecule along the particular oxygen axis to an angle 180. So if you rotate the molecule, you will be getting the second orientation, which is superimposable to the original one. So this is called C21. That means we have carried out C2 operation once to get second orientation. After getting second orientation, if you perform C2 operation another time, you will be getting structure number 3. Now there are 3 structures. If we look into the structures, we can come to the conclusion structures 1 and 2 are said to be symmetrical, or they are having these equivalent orientations. But if you take structures 1 and 3, they are not only equivalent, they are also identical. So in a molecule having a C2 axis as one of the symmetry element, if you perform C2 operation twice, you will be getting an identical orientation. Similarly, second case is our BCl3 molecule. It is just given in this diagram. In BCl3 molecule, if you look into the molecule, actually there are 4 rotational axes. They are 1 C3 axis and 3 number of C2 axes. This 1 C3 axis is exactly perpendicular to the plane of the molecule, because you know very well BCl3 is a planar molecule. All these 4 atoms, namely 1 boron and 3 chlorine, are lying on one plane. So if you draw a line which is exactly perpendicular to the plane of the molecule through boron, that will be called as a C3 axis. So C3 axis is perpendicular to the plane of the molecule. Whereas if you take other 3 C2 axes, all the 3 C2 axes are lying on the plane and they are all passing through the corresponding boron chlorine atoms. So I have given the examples chlorine 1, chlorine 2, chlorine 3. If we draw a straight line via boron and one chlorine, that is called one of these C2 axis. Similarly, another boron with the Cl2, second C2 axis. Boron with the third chlorine will be having the third C2 axis. So like this, there are 3 C2 axes which are lying on the plane and only 1 C3 axis which is exactly perpendicular to the plane. Along this C3 axis, if you perform the rotation to an angle 120, then you will be getting equivalent orientation which is given in the structure number 2, that is called C31. Then once again you perform C3 operation second time, that is given by structure number 3. Once again carry out C3 operation third time, you will be getting structure number 4. So like this I can give 4 orientations. Among the 4, structures 1, 2 and 3 are called equivalent orientations, and the structures 1 and 4, which is also equivalent to number 1, are called identical orientations. So in the same BCl3 molecule, I can perform one more operation, that is called the C3 operation in the anti-clockwise. So the thing which I have already mentioned are only the corresponding clockwise rotation. But if you perform anti-clockwise rotation, one cannot expect the same orientation which you have obtained for the clockwise rotations. So as far as water molecule is concerned, whether you are performing the operation in the clockwise or anti-clockwise, it is immaterial. In both the cases, we will be getting same orientations, same symmetrical orientations. Whereas as far as our BCl3 is concerned, which is having cyclic structure, if we perform the operation via the clockwise direction, we will be getting one set of orientations. If you perform the operations, namely rotation, via the anti-clockwise directions, we will be getting the another orientations. From the diagram, we can come to the conclusion as far as BCl3 is concerned. So C31 is equivalent to C3 minus 2. So like this, I can quote number of examples. Similarly, in the second diagram I have given the operations pertaining to C2. The C2 operation, if you perform C2 operation, suppose if you perform the C2 operation via B and Cl1, the Cl1 will be retained and Cl2 and Cl3 will be interchanged. Similarly, if you perform the C2 operation via chlorine number 2, 2 will be retained and chlorine 1 and 3 will be interchanged. Similarly, if you perform the operation C2 along the third chlorine atom, Cl3 will be retained and 1 and 2 will be interchanged. All those things has been given in the particular diagrams. So second case we have seen BCl3. Third example which I can quote is the simplest molecule. Molecule we know very well, there are only 2 hydrogen atoms. That means 2 hydrogen lamellin 2 balls has been combined together through a single covalent bond. So even though the molecule is very simple, one may think the number of symmetry elements present in the particular molecule will be very small, but it is not the case. In hydrogen molecule, actually if you take the HH bond angle, the HH bond angle is representing a C infinity axis. That means what is called C infinity? That means if you rotate the molecule to an angle approximately equivalent to theta, you will be getting an equivalent orientation. So now here bear in mind, don't say theta is exactly equal to 0, but it is not 0. Theta is tending towards 0. When theta is tending towards 0, you know very well n is equal to 360 by theta. So 360 by almost equivalent to theta means you will be getting the infinity. Hence HH bond axis is representing your C infinity axis. Similarly, you take all the diatomic linear molecules like O2 molecule, N2 molecule, as well as Cl2, Br2, and also you take our acetylene also. All the molecules are said to possess one axis called C infinity axis, namely your HH bond axis. Besides your C infinity axis, in hydrogen molecule, we are having C2 axis. So now if you look into the molecule, one can come to the conclusion. First, we are having 3 number of C2 axes, which are all equivalent to your 3 conventional Cartesian coordinates, namely x-axis, y-axis. These 2 are called your conventional C2 axis. But if you look into the molecule, actually we are having infinite number of C2 axes. All the C2 axes are passing through the center of the molecule, namely HH bond axis center point. So net result, in your hydrogen molecule, we are having one C infinity axis and the infinite number of C2 axes. If you take the same our molecule HCl, it is having almost similar structure. What is the main difference? I have replaced one hydrogen atom by one chlorine. Because of the replacement of one of the hydrogen atom by chlorine, we are having a same linear structure and the C infinity axis will be present. But what about your C3 axis? In your hydrogen molecule, just now I told you there are infinite number of C3 axes. But in the molecule HCl, if you look into the molecule, we can come to the conclusion not even one C2 axis is present. All the C2 axes which are present in H2 molecule will disappear when you move from your H2 to HCl. That means when you move from H2 to HCl, the symmetry order will completely collapse. Similarly, if you take this CO2, there also we are having a C infinity axis, and also we are having a 2 number of C2 axis. Then if you take the another molecule called ethylene, in ethylene also all the 3 conventional axes called your x-axis, y-axis and z-axis are behaving as C2 axis. If you rotate the molecule along this axis to an angle 180, you will be getting an equivalent orientation. So I can claim the presence of 3 number of C2 axes present in the molecule called ethylene. But if you take the molecule trans-dichloroethylene, in this molecule we are having only one C2 axis. The other C2 axis will be disappearing because the molecule is having lesser number of symmetry. The axis which is exactly perpendicular to the plane of the molecule is called C2 axis. The axis which we are lying on the plane of the molecule will disappear. Then after seeing the different examples for your rotational axis, we have to see the assignment of the axis. Assignment of axis means in these Cartesian coordinates we are taking 3 axes x and y which are lying on the plane, and z is always perpendicular. The same convention need not be or cannot be applied to a particular molecule. So for each and every molecule, depending upon their structure and depending upon their orientation, we have to fix which one is z, which one is x, which one is y in the same order. So there are 2 sets of rules. Each set is having 3 rules. First one is assignment of z-axis. The z-axis can be assigned by following the 3 rules. Number 1, if the molecule is having only one rotational axis, that axis should be called as z-axis. Follow me? If the molecule is having only one rotational axis, that axis should be called as z-axis. Number 2, if the molecule is having more than one rotational axis, then axis which is having the maximum fold or highest order will be called as z-axis. Number 3, if the molecule is having more than one rotational axis of the same fold or same order, then the one which is passing through maximum number of atoms will be called as z-axis. So far we have seen the 3 rules which will be very useful for the assignment of z-axis. So by following the 3 rules, one can give or one can assign z-axis. After assigning the z-axis, then we have to move to assignment of x-axis. Now for assignment of x-axis, the following 3 rules will be very helpful. Rule number 1 says, if the molecule is planar and the z-axis is lying on the plane, then x-axis should be perpendicular to the plane. Number 2, the molecule is planar and z is perpendicular to the plane, then x-axis should lie on the plane so as to pass through maximum number of atoms. Number 2. Then number 3, rule number 3 says, if the molecule is non-planar, assume a plane containing large number of atoms at the plane of the molecule, and then the above rules, namely 1 and 2, should be followed in the same sequence. So by following the 3 rules, we can assign the x-axis. So first we have assigned the z-axis, then we have assigned the x-axis. You know very well, in the Cartesian coordinates only there are 3 axes. So among the 3, I have fixed, I have confirmed 2 things, namely our z-axis as well as x-axis. Automatically the third one which is left will be assigned the y-axis. That's why there is no definite rule for the assignment of y-axis. So before applying the rule, one have to follow one important thing. First you take the molecule. For all the molecule, whether the molecule is having a center of symmetry or not, there will be a point through which the center of gravity is acting. So you consider the center of gravity of the molecule, you visualize the molecule, and then you can come to the conclusion where its CG is acting. The CG point of the molecule first should coincide with the origin for the Cartesian coordinates. So that is first thing. You take the molecule, consider your center of gravity of the molecule. The center of gravity of the molecule should be coincident with the origin for the Cartesian coordinates. Then after placing this center of gravity on the origin, follow the 2 sets of rules for the assignment of z-axis. So you place the center of gravity of the molecule on the origin of the Cartesian coordinates, and then you assign z-axis and then x-axis, followed by this one we can assign the y-axis. So as I already mentioned, there is no definite rule for the assignment of y-axis, because once if we fix both your x-axis as well as z-axis, automatically third one left will be called as the y-axis. So by following the rules, we can assign the axis for a different molecule. In the diagram, I have given the entire thing. So I have taken few examples. They are BCl3 molecule. In the BCl3 molecule, the axis which is passing through the central carbon atom and which is exactly perpendicular to the plane of the molecule. So in BCl3, you know very well the molecule is planar. All the 4 atoms are lying on the same plane. The axis which is exactly perpendicular to the plane of the molecule and which is passing through this boron atom will be called as C3 axis. So since it is having the highest fold, because other 3 are called your 3C2 axis, so C3 is having the highest fold or maximum order, therefore this should be assigned Z axis. So the axis which is exactly perpendicular and passing through the boron will be called as Z axis. Then coming to the X axis in BCl3, since the molecule is planar and Z is perpendicular to the plane, X axis should lie on the plane so as to pass through maximum number of atoms. That means the axis which is passing through one boron and another chlorine will be called as X axis. Third one left will be called as the Y axis as far as your BCl3 is concerned. Second case, you take your ethylene. In ethylene molecule, as I already mentioned, there are 3 number of C2s. Since all are having the same fold or same order, then you have to apply the rule number 3 for the assignment of Z axis, which states if the molecule is having more than one rotational axis having the same fold or same order, then one which is passing through maximum number of atoms should be called as Z axis. As per this one, the axis which is passing through 2 carbons will be called as Z axis, which has been given in the diagram. That is called Z axis. You know very well, molecule is planar and Z is passing through the plane of the molecule, then X axis should be perpendicular with the plane. It is also given in the diagram. That is called as X axis. Third one left, which is bisecting the carbon-carbon double bond, will be called as Y axis. Third example, your benzene. Benzene, the molecule is planar. All the 6 carbon atoms and 6 hydrogen atoms are lying on the same plane. And the axis which is passing through the center of the molecule, which is also perpendicular to the plane of the molecule, will be called as C6 axis, which is the highest fold. Therefore, this axis will be called as Z axis, which has been given in the diagram. So now molecule is planar, Z is perpendicular to the plane, therefore X axis should lie on the plane so as to pass through maximum number of atoms. That has been also been given, so that is called as X axis. Third one left is called Y axis. Fourth example I have given your trans-dichloroethylene. For trans-dichloroethylene, the axis which is exactly perpendicular to the plane of the molecule passing through the center is called Z axis. The axis which is passing through 2 carbon atoms is called X axis, and third one which is bisecting the carbon-carbon double bond is called Y. Coming to the linear molecules, either nitrogen or hydrogen or chlorine, for all the molecule, the nitrogen-hydrogen double bond axis, triple bond axis will be called as Z axis, which is also called C infinity axis. Then the one which is exactly perpendicular to this molecule will be called as X axis. Third one which is bisecting the nitrogen-hydrogen triple bond will be called as Y axis. Last example, water molecule. In water molecule, the axis which is passing through the center oxygen atom, which is lying on the plane, is called Z axis. Next one, your X axis. X axis is exactly perpendicular to the plane of the molecule, so that is called X. Third one left will be called as Y axis. So I have given more number of examples to understand the assignment of axis for the particular molecule. So now so far we have seen 3 important symmetry elements with the corresponding examples with the corresponding symmetry operations. And also in the last case, namely our axis of symmetry, I have given the 2 sets of rules which are very useful in assigning your Z axis as well as X axis. With this we can conclude. Next thing we can continue in the next lessons. Thank you very much.